Alright, I'm going to be doing a little mini lecture on Banach spaces, and hopefully by the end of the lecture I can define, at least at some sort of surface level, of what a Banach space is. So in order to get there, we're going to have to go through a few other definitions in order to build this one. And yeah, I don't know, let's get started. So the first thing I want to talk about before we can start talking about Banach spaces is the idea of a norm. And so you remember that in a given vector space, a norm is something that we can do in certain vector spaces that measures the length of vectors. And so it's a really important thing, and you can imagine that going forward, it's a really useful tool to do certain analysis on vector spaces. And ultimately, Banach spaces are a type of vector space that we can do certain analysis, whether that's real or complex analysis, on, because they have certain analytic properties added in. And one of these that we need to talk about is the idea of having a norm. So, if you recall that if we let, say, V be a vector space, right, then we can say then the map, which we usually show as these long lines, so that map from V to the non-negative reals is a norm if we have these following properties that hold. So V, so if, say, given vector in that vector space, if the norm of that is 0, well, that's true if and only if the vector itself is 0. So for some vector in our vector space. The second property that we need in this definition of a norm is that if we are given the norm of some scalar times a vector in our vector space, well, that's going to equal the absolute value of that scalar multiplied by the norm of the vector. Again, that's for a scalar and some vector in our vector space. And finally, 3, we're going to get that, say, given the norm of a sum of vectors in our vector space, that is going to be less than or equal to the norm of each of them summed together. Let me just make that a little cleaner. So the norm of V plus the norm of W, and that is for, say, V and W in V. So you can see that this is actually the triangle inequality, something that comes up a lot in analysis. So that is the definition of a norm, and it might look a little abstract right now, but we actually came across some easy norms to understand, and let's just look at an example of a norm that we came across in class, which is a norm in Rn. So example, we're going to do Rn. So let's just look at some vector in Rn, and that vector is, say, defined with components v1 up to vn maybe. So the norm of V in the case of Rn, if you recall, we defined as the square root of the sum of each of its components squared. And this is measuring really the length of this vector in Rn. And so yeah, we can also do this in the complex numbers in Cn, say, and just all that we need to change here would be that we're taking the square of the modulus of each of the components of that complex vector. So that's an example of a norm we came across, and a norm is obviously a really useful thing. And vector spaces that have norms, or that you can define norms on, are sort of special in that way. And we give them a special name, which is a normed vector space, or just a norm space. So if we can, I'll just write this down, if we can define a norm, say, on V, then we say that, and we use this notation with these parentheses, that V comma, this function or this norm is a normed vector space, or just a normed space. I'll write normed space here. Right, so we have this. So it's important that we have this kind of idea of what a norm space is, because a Banach space is a special type of norm space. So we have this concept of norm and a norm space, this idea of the length of a vector. But what if we were to look at the length between two given vectors in a vector space? Well, that's something that we also kind of came across, we touched on. And that idea is wrapped up in the concept of a metric. So, what a metric is it's a function, just kind of like a norm is, that measures the length or distance, a distance function, between two vectors in a vector space. And in fact, you can extend this into sets. You can define metrics on certain sets, so it's not just in vector spaces. But say we let's say, I'll say it's a set. Let A be a set. Of course, that set may be a vector space. Then the map, so the map, say D from the Cartesian product of A, so it's going to have two arguments in this function, to the non-negative reals, is a metric if we have the following that holds. So we have that 1, basically the metric of x, y, or I guess the distance between x and y, is equal to 0 if and only if x equals y. And this is for x and y in our set A, which might be a vector space. 2, we have that, the distance between x and y is going to be equal to the distance between y and x. So that means that this map is symmetric. Map is symmetric. Just write that down. And the third property that we need to be able to define a metric on this set, or to show that this function is a metric, is that given, say, the distance between x and y, that's going to be less than or equal to the distance between x and z plus the distance between y and z. And again, this is for x, y, z in our set. And this is also the triangle inequality popping up as the third property of this definition of a metric. And you can probably see that there's a lot of similarity in how this definition looks to that of a norm. And it is similar because norms and metrics are kind of really intimately related. In particular, any normed space is a metric space. And so I'm just going to define what a metric space is. And basically, a metric space is kind of analogous to what a norm space is. And a metric space is really just a set that we can define a metric on. So in this case, if we could define a metric D on A, then A is a metric space. So if we're given a norm, so a norm space, so given, say, we're going to be just dealing with vector spaces in the sense. So given, say, a norm space, so we're given a norm space, then we say that V and this function, which we'll put this norm as its index, is its associated metric space. So you do metric space. And so every norm space is a metric space. And you get those norm properties from just, or I guess, sorry, you can get these metric properties from the norm properties. You can show that they follow if you have a norm in a vector space. So we have now that we have the idea of a norm space and the idea of its associated metric space that's defining the length between vectors in that vector space, or the norm space. And so we're pretty close to being able to define a Banach space in totality. But there's one more little thing that we need to talk about, which is the idea of completeness, and specifically completeness of a metric space. So I'm just going to write this here. Completeness of a metric space. So this is kind of where our the realm of analysis is intersecting here with what we're talking about in linear algebra, completeness of a metric space. So usually when we're defining completeness, we're going to be defining it as Cauchy completeness in this definition, just because that way of defining completeness works well in this definition. And so we can say that a sequence, so say we're given some sequence, maybe x1, x2, and it's of some length, perhaps, or it's I guess it's infinite. So given a sequence in a metric space, a sequence in a metric space is what we call Cauchy complete, or really just complete. We're just using the idea of Cauchy completeness in this definition because it works well if for all epsilon greater than 0, there exists some natural number n such that basically for all m and n in the natural numbers, we have that the distance between the sequence x indexed at m and sequence x indexed at n is less than epsilon. So we can make it arbitrarily small. And that idea of making things arbitrarily small, this idea of completeness is important because it kind of allows us to take limits freely in a certain metric space. In that there's no gaps in this metric space, and if we take a limit, we're going to stay in that space. And a good example of a complete metric space, or just a complete field, I guess in general, is the reals. That you can take limits, there's no gaps in the reals, it's uncountably infinite, right? So we'll always have a real limit if we're taking limits of sequences in the reals. And we have that every Cauchy sequence in the reals, I should say this is Cauchy, haha. So it's not, the sequence itself isn't complete, but the sequence is Cauchy, and if we have that if all Cauchy sequences converge, then the metric space, then our metric space is Cauchy complete or just complete. Metric space is complete. So this is kind of the last thing we need to be able to define when talking about a Banach space. We want a complete metric space so that we can take limits and we can just kind of do analysis in a more free way without thinking about a lot of different cases. So now that we've got our kind of three ingredients, which is the idea of a norm space, the idea of an associated metric space to that norm space, and the idea of a complete metric space, we can finally define a Banach space. So I'm going to write this definition. So, say let some vector v and this norm be a normed vector space. With an associated metric space, so I'll show like that, that is complete, then we say that the norm space is a Banach space. And that is our definition. So we've been able to define what a Banach space is, and that is kind of a cool definition. It seems a little abstract, but we can just take a really easy example. So say, let's just look at the real number line. So for the reals, we can define this as a norm space because our norm is just the absolute value function. That's going to give us a positive distance or length of a vector in R on the real line. So our norm is our absolute value function, and of course our metric is just going to be, say, the absolute value of the difference of two vectors, you could say, one-dimensional vectors, in R. So we have a norm, we have a metric, and we know that R is complete. And it's kind of the prime example of a complete field. So all of these ingredients add up, and it gives that R is a Banach space. And there's lots and lots of examples of Banach spaces, but hopefully that this little mini lecture sort of explained how we can define them, and I'm definitely excited to learn more in this field of functional analysis.